Hi everyone, welcome to your class. We were about to study atomic structure. So, got a class is about atomic structure, structure of the atom, atomic structure, hydrogen-like atoms, structure of the hydrogen atom. It's known by several different names in the books that you'll study. So, let's begin. Structure of the atom. You see, towards the beginning of the last century, people discovered that there are what is called as subatomic particles. There are several reasons for saying that there are subatomic particles. First of all, chemical reactions they happen because of the exchange of electrons, and this was very well understood that all the bonding between atoms happens because either electrons are shared or electrons are given ionization. If you rub a comb on your hair, then there is a loss of charge, but otherwise the comb is neutral. So initially, people used to think that rubbing creates charge. The act of rubbing two things together, it creates charge. But then later on, people realized that all matter is neutral. Okay, so all matter is neutral, but it still has two kinds of charge in it. It has positive charge and it also has negative charge. In those years, somebody also discovered that there is a third kind of particle, which is a neutron. Okay, so there are protons, electrons, and neutrons, and all of these three things they combine and form the basic unit of matter that makes up almost everything. So everything is made up of atoms. Even molecules are made up of atoms. Our bodies are made up of molecules. Molecules are made up of atoms. And atoms are made up of three particles: protons, electrons, and neutrons. So protons they have positive charge, or they have a certain kind of charge that is called positive, and the mass of a proton is just basically one. Electrons have negative charge and the mass of an electron is zero. And neutrons have mass, but they do not have any charge at all. So, when atoms consist of three subatomic particles, the obvious question arises how an atom is how these particles are arranged inside an atom. So, out of all the models that were there are a few models that are wrong, and it is useful to study them just to know what went wrong. For example, the plum pudding model, which basically says that an atom is like ice cream, and all the electrons in an atom are like cherries or the fruits in an ice cream. Okay, that is wrong. That's because if you have an atom that is that's completely like an ice cream, all the positive charge is like forming a ball, and you embed it with negative charge, then the positive charge and the negative charge they strongly attract each other, and they produce a very strong force of attraction. Okay, they produce a very strong force of attraction because of which electrons cannot escape and they cannot take part in chemical reactions. So the plum pudding model is obviously wrong. Rutherford came up with an experiment where he takes a gold foil. Okay, if you read your books, you'll see this diagram in the books as well. He takes a gold foil and he surrounds the gold foil with a glowing screen. The screen will glow if any electron or any subatomic particle like a proton or something hits it at some particular speed. So he took a gold foil and he surrounded it with a screen, and then he takes a source of fast moving alpha particles or heavy neutrons, they are also subatomic particles, and he fires the gold screen with it. So what he was expecting is either all of these particles should return back, all of these particles they should just return back, or maybe all of these particles should just go forward. One of the two things. But instead of this, what he actually noticed or he discovered was these particles they are scattered in all directions. So the only possible reason that this thing can happen is, first of all, understand why would they come back. They would come back if an atom was a solid sphere. If an atom was a solid sphere and you fire a particle towards it, the particle has to bounce back. Or instead, if the atom is mostly like an ice cream, then the particle should just pass through the atom and they should come out at the other side. But instead, an atom is neither this nor is it like an ice cream. It's basically empty space with a very solid sphere at the center. The reason that all these particles can get scattered to so many directions is that the center of an atom is mostly solid. So if you fire particles towards the center of an atom, either the particles will pass through, they will miss, and that is how there are a large number of particles right in front, or these particles will hit the center spot on and they will return back, which explains the particles that come over here. Or maybe they will hit the center at some angle and they will get deflected, which explains the particles over here. So Rutherford's idea was that an atom is mostly empty space. An atom is mostly empty space, but the center of the atom contains all its mass. So he called the center of an atom nucleus. Okay. He later on also proved that because alpha particles are positive and they are repelled by the nucleus, they bounce back from the nucleus. The nucleus also has to be positively charged. So that means that electrons rotate around the atoms in circular orbits or in whatever kind of orbits. Scientists came up with a model that electrons have to rotate in circular orbits because the attractive force from the positively charged nucleus, this electrostatic force of attraction, can provide the centripetal force required to travel in a circular path. Okay, so we can say that K Q1 into Q2 divided by R square is equal to mv square divided by R. So what I'm basically saying is the electrostatic force of attraction from the positively charged nucleus or between the positively charged nucleus and the electron is responsible for electrons to go around in a circular path. You know all of these things from chemistry, but I'm just teaching it to you in a very patient and proper way. So this is the first idea about the model of the atom. The center of an atom is positively charged, and all the electrons are rotating around it in circular orbits, and that's because of the electrostatic force of attraction. This unfortunately means that the electrons are constantly accelerating, and this fact you may not understand right now, but an accelerating charge continuously emits electromagnetic waves. I did mention this fact to you when I was teaching you EM waves, that an accelerating charge continuously emits electromagnetic waves, which means that it is going to lose energy because electromagnetic waves, they consist of energy, right? So an electron is going to lose all of its energy, and then it is eventually going to fall into the atom, something that does not happen. So over here, Niels Bohr suggested three postulates. There are the three Niels Bohr postulates. So a postulate is something that you do not know why it is true, but you say that it's nevertheless true based on experimental facts, so that it can justify the outcome of an experiment. Okay. So he agreed with the first thing, that electrons rotate around the atom in closed circular orbits because of the electrostatic force of attraction. The second idea was that the angular momentum of these electrons is a constant multiple of h by 2 pi, where n is what is called as the principal or the orbital quantum number. Okay, so he said that around an atom, electrons rotate in specific paths, kind of like the rows inside a stadium. So there is the first line of seats, there is the second line of seats. There is no in between space. So either n is 1 or n is 2. So there are specific fixed values, kind of like the steps on a staircase, where there are electrons. In between, there are no electrons. Okay, so he said that all of these orbitals, the energy of the electrons in these orbitals, their angular momentum, the L stands for the angular momentum. All of these values are actually quantized. They have specific values. And then the third thing, that the energy of an electron in a specific orbital is fixed. And not only is the energy fixed, but also the energy is again quantized. So with this, quantum theory came out. So he's basically saying that in an atom, all these electrons, their angular momentum is quantized. Keep in mind what I said about quantized. Quantized means something is not only fixed, but also it can have particular values. Kind of like, milk packet. So you have a milk packet of 100 ml, you have a milk packet of 250 ml, you have a milk packet of 500 ml, you have a milk packet of 1 liter. You cannot get a milk packet of 1230 ml. That's not possible because that is not what the companies manufacture. Okay. So there are specific values and there is nothing in between those values. So there is no 160 ml. There is either 100 ml or there is 200 ml. So that kind of an idea is what is called as quantization. So our job over here is to prove the relation between R and N, something that we will use in solving problems. It is well known that as a result of these postulates, R is proportional to N square upon Z, and E, the energy of an electron, is proportional to Z square upon N square. So all of today's class is about deriving this and seeing some applications of it and seeing some results of it. and basically studying it in a lot of detail. So let's start. The first Bohr postulate says that K, which is the electrostatic constant 1 by 4 pi epsilon 0 into Z into E square divided by R square. So this is just basically Coulomb's law, is equal to m omega square R. I've written mv square by R as m omega square R, which is the centripetal force on an electron. Okay. So the centripetal force on the electron is m omega square R. The next thing is the angular momentum of an electron. So the angular momentum of an electron is equal to m r square omega, and this value is quantized and it is equal to nh divided by 2 pi. Okay, so these are the first and the second Bohr postulate. Our plan is to take omega from one of these equations, from the lower equation, and to substitute it into the upper one. Okay, so omega is equal to nh divided by 2 pi m r square. Now you take omega from this equation and you put it into that one. So you'll get k z e square divided by r square into mr into n square h square divided by 4 pi square, okay, m square r to the power 4. So r square, r and r to the power 4, they basically cancel out to give you r. And r is equal to, see all these remaining terms, most of them are constant. So I'll write n square outside. And then you have h squared divided by 4 pi square m. And from here you'll have k e square divided by z. So all of these terms over here, they are basically constants. In fact, you can simplify this a little more by saying that k is equal to 1 by 4 pi epsilon 0. So 1 divided by 4 pi epsilon 0. So 4 pi cancels with 4 pi square to just simply give you pi. So you can write that r is equal to n square divided by z h squared epsilon 0 divided by pi m e square. All of these terms on the right, h, epsilon, pi, the mass of an electron, and the charge of an electron, all of these terms, they're actually constants. So it's a very good idea to put n is equal to 1, z is equal to 1, and directly measure the radius of such an orbit. So what is n? N is the orbital quantum number, or it is also called as the principal quantum number. And z is just basically the atomic number. So if you put n is equal to 1 and z is equal to 1, that just basically means the first orbit of hydrogen atom, the first orbit of the hydrogen atom. So R1, or basically R0, like it is called as the ground state, is equal to h square epsilon 0 divided by pi me square. This is measured to be 0.53 angstroms experimentally, and it is called as the Bohr radius. इस चीज को हम लोग कहते हैं, this is the Bohr radius. बेसिकली लोगों ने क्या करा, they wrote down the formula r is equal to n square by z. इतने सारे constants होते हैं, they derived it out of all this, like, you know, physical theory. And then they went to the lab and they did an experiment. They said, like, if r is equal to n square by z h e square, we can't multiply all this stuff, so let's just find out what happens if n is equal to 1, z is equal to 1. So that happens to be the Bohr radius, and this formula is very concisely written as n square r0 by z. Okay, so this is the value, or this is the formula that we'll use in all the questions where the radius of an atom is required. So the radius of an electron in an atom is n square divided by z multiplied by r0. ठीक है, r0 को क्या कहते हैं? r0 is called as the Bohr radius. It has a value of 0.53 angstroms. That's the first thing. Second thing, what is the energy of an electron? The energy of an electron is obviously the sum total of its kinetic energy and its potential energy. Potential energy कितना होगा? It is equal to k q1 into q2 divided by r. ये तुम्हारा potential energy. Kinetic energy is equal to half mv square. Now from the first slide where we wrote k into z e into e divided by r square is equal to mv square divided by r. You must have noticed that mv square is equal to kze into e divided by r. What is this? This is minus 2. What is mv square? That is just 2 times the kinetic energy. So this gives us the simple relation that k is equal to minus u by 2. This relation is important. So we can write total energy is equal to kinetic energy plus potential energy. और ये कितना होगा? kinetic energy is equal to minus u by 2 और potential energy is equal to u. तो total energy हो जाएगा simply u by 2, u minus u by 2 which is equal to simply u by 2. ठीक है, ये तुम्हारा total energy है. तो u का वैल्यू कितना है, k इंटू जेड इंटू ई डिवाइडेड बाई आर. तो अपन उसका वैल्यू यहाँ पे लिखते हैं, इट इज इक्वल टू हाफ इंटू माइनस, ठीक है, इंटू के इंटू जेड ई स्क्वायर डिवाइडेड बाई आर. और आर का वैल्यू कितना है, आर जीरो एन स्क्वायर डिवाइडेड बाई. I'm basically trying to write down a proportionality here. So t is equal to minus, there is a minus, there is k, there is r0, and there is e square, and there is a 2 also. So there are all of these constants. And apart from that, there is z square divided by n square. So once again, if you put n is equal to 1 and z is equal to 1, then you will get t is equal to minus 13.6 electron volts, which is basically the energy of an electron, the energy of an electron in the first orbit of the hydrogen in n is equal to 1 of the hydrogen atom. Okay? So this amount of energy is called as 1 Rydberg. We'll come to this at the end of the class today. Rydberg क्या होता है, इसको Rydberg क्यों बोलते हैं? It's named after Johannes Rydberg, who gave a equation of 50 using. So that amount of energy is called as 1 Rydberg. तो अपन ने क्या किया यहाँ पे? We derived two relations pretty nicely. And then we went to the lab and we found out what are the natural values for those constants. So in one case, it is 0.53 angstroms, that is the radius of the first orbit of an hydrogen atom. And in the other case, we found out the amount of energy of that orbit, which is equal to 13.6 electron volts. ठीक है, 13.6 electron volts. तो ये जो दो equations हैं, they are fundamental for solving the chapter. So R is equal to R0 into N square divided by Z, and E is equal to E0 into Z square divided by N square. तो इससे पहले कि अपन आगे बढ़ें, let's understand कि equation apply किसको करते हैं. ये equations apply करते हैं to something that is called as a hydrogen-like atom. These equations apply to something that is called as a hydrogen-like atom. Hydrogen-like. So what are hydrogen-like atoms? So hydrogen-like atom is something that has Z protons, or any number of protons you want, but it only has one electron. Okay. So you are taking hydrogen. The hydrogen obviously itself is a hydrogen-like atom. But helium has two electrons. So if you remove one of the electrons, you ionize helium, singly ionized helium, will become a hydrogen-like atom. If you take lithium, then lithium has three electrons. In its two orbitals, it has three electrons. But if you doubly ionize lithium, then it is going to become a hydrogen-like atom. In general, we're talking about hydrogen-like atoms. If you take any general atom, then the effect of all the electrons between that electron and this atom would be to subtract. मतलब अगर इसके बीच में there are x number of electrons, then you should write z protons minus x electrons, which is just z minus x. And then you should solve for the radius of that. Normally you will not be asked that. But hydrogen-like atoms जो होते हैं, उनमें न्यूक्लियस होता है, न्यूक्लियस में बहुत सारा पॉजिटिव चार्ज होता है, और बाहर बस एक ही ऑर्बिटल होता है जिसमें इलेक्ट्रॉन रोटेट करता है. ठीक है, तो ये होता है तुम्हारा हाइड्रोजन लाइक एटम. और हाइड्रोजन लाइक एटम में वो दोनों फॉर्मूलाज अप्लाई करते हैं. Now the point is, what is the proof of this? What is the proof कि ये सारे whatever I told you right now is actually correct. So the proof of all of this comes from something that is called as emission and absorption spectrum. Emission and absorption spectrum of atoms. So that is the remaining part of this chapter. So once you are done with the emission and the absorption spectrum in the case of atoms, you can just straight away start doing problems. But इसके भी पहले, do you remember about the photoelectric effect? If you take an atom, the atom has some number of protons at the nucleus, and electrons are rotating around this atom. If you put photons on this thing, अगर तुम इस पे लाके, if you put some photons of light, every electron absorbs a photon and then it jumps. The minimum amount of energy this photon must have is a particular quantity. That is because the electron has a negative energy in this orbit. Negative energy मतलब ऐसे मान के चलो there is zero energy, and negative means it's like a pit. So the electron is inside this pit. तुम आगे चल के पढ़ोगे तो you'll call this thing a whirlpool. Okay? तो electron को ये specific amount of energy चाहिए. This thing is your threshold wavelength, or this thing is your threshold frequency. जो भी तुम बोलो, it is your work function power. It requires this specific amount of energy. The key idea here is it's a specific amount of energy, not some random value. That amount of energy is quantized. So the idea I'm trying to give you here is photoelectric effect is a very good proof that the energy of electrons in an atom is fixed or it is quantized. ठीक है, तो एक प्रूफ आता है फोटोइलेक्ट्रिक इफेक्ट से कि एक पर्टिकुलर अमाउंट ऑफ एनर्जी अगर हम लोग सप्लाई नहीं करेंगे तो इलेक्ट्रॉन एटम से एक्साइट होकर बाहर नहीं निकलेगा। ठीक है, so photoelectric effect is one proof. The other proof is emission and absorption of light by atoms, जिसको हम लोग बोलते हैं emission and absorption spectrum. So वहाँ पे idea ये है कि in an atom when all of these electrons are rotating around the nucleus, these electrons they have particular amount of energies, so their energies are basically negative. ठीक है, they have particular amount of energies, mostly negative. If you provide a very large amount of energy to the electron, तो ठीक है, the electron is going to escape and you are going to have photoelectric effect. But if you do not provide such a large amount of energy, then the electron is going to jump from one, like from its orbital to a slightly outer orbital. And वो कहाँ तक jump करेगा ये नहीं पता, but it will jump from one orbital to an outer orbital. Like इसके बाहर जो भी orbital है, it will jump from an inner orbital to an outer orbital. So in an atom there are going to be lots of these orbitals. So an electron is going to jump from its own orbital to an outer orbital, provided that wherever this electron ends up, जहाँ कहीं पे भी जाके ये इलेक्ट्रॉन पहुंचेगा वहाँ पे कुछ ना कुछ तो ऑर्बिटल होना चाहिए. There should be something over there. So if this electron is like it's going to jump and there is no orbital over there, basically this electron is going to return back. It's going to come. तुम लोगों ने केमिस्ट्री में पढ़ा होगा. This jumping out is called as excitation, and this jumping in is called as de-excitation. So an electron can either jump out. If it finds an orbital, very fine. It will go and stop at that orbital. Like in this case, it is finding an orbital, so it will stop over there. But if it doesn't find an orbital, it will just fall back to its original orbital. और इसने जो भी फोटोन अब्जॉर्ब किया होगा वो उतना फोटोन ऑफ लाइट को री-एमिट कर देगा. बात समझ में आ रहा है? There is an atom. Like imagine that there is a staircase and it's pitch black and you're trying to climb that staircase. You might have some very hard experiences with something like this. So if you blindly try to climb up a staircase, you're going to put your foot up. Now, if there is a stair, good luck. If there is no stair, then you're going to slip and fall. Same चीज electrons के साथ है. In fact, I want you to have this understanding for your further studies in college. Whenever you think of quantum physics, think of a staircase or think of constant values. Okay, in a staircase, all these stairs they have fixed positions, just like that. The orbitals in a number, they have fixed and very well-defined, definite positions. बड़े specific positions होते हैं space में. तो electron जैसे ही jump करता है from one orbital to another orbital, it requires a very particular amount of energy. अगर इससे कम या इससे ज़्यादा एनर्जी तुमने इलेक्ट्रॉन को प्रोवाइड किया तो ऐसा नहीं होगा कि the electron will somehow correct and like anyway jump. No. Even if it has too much energy, it will not be able to jump because wherever it will fall, there is nothing to put your foot, right? If you put your leg too much up the staircase and there is no stair over there, you're going to fall. In the same case, like just like just like this case, in the case of an electron, if you give too much amount of energy, the electron will go and it will come back and it will re-emit all of that energy. So there is an absorption and there is an emission spectrum. Absorption happens when पहले तो अपन सारे कलर्स को थोड़ा बहुत ड्रॉ करने की कोशिश करते हैं. I don't have the patience to do that, but think of violet, and from violet think of all of these colors all the way up till red. So all of it together it makes up the spectrum. Somewhere towards the middle of the spectrum you have green, somewhere towards the right of the spectrum you have yellow, somewhere towards the right of that you have orange, and somewhere towards the left of this somewhere you have blue, and somewhere towards the left of that blue you have an indigo. Okay, this is kind of your spectrum over here. The point is the actual spectrum is kind of like a band, so there are many frequencies, and it also extends into ultraviolet and it also extends into infrared. Okay, so if you put the whole of light in a sample containing a few atoms, so each of these things, violet is around 400 nanometers and red is around 800 nanometers. So each of these wavelengths, it carries a very particular amount of energy. Now, if that energy exactly matches the gap between one orbital and another orbital, तो एक एटम में एक ऑर्बिटल और दूसरे ऑर्बिटल के बीच में जो एनर्जी का गैप, लेट्स गिव यू अ वेरी स्पेसिफिक एग्जांपल. हाइड्रोजन का पहला ऑर्बिटल 13.6 इलेक्ट्रॉन वोल्ट और दूसरा ऑर्बिटल 3.4 इलेक्ट्रॉन वोल्ट, मतलब इन दोनों के बीच में 10.2 इलेक्ट्रॉन वोल्ट्स का फर्क है. If you put 1240 divided by 10.2, you remember 1240? So you'll get approximately 118 nanometers, approximately 118, approximately 120. अगर यहाँ पे कहीं पे 120 नैनोमीटर का जो जगह है, that exact 120 is not going to be present anymore. All of it is going to get absorbed by the atom. ठीक है, मैं इसको मिटा दिया accidentally. All of it is going to get absorbed by the atom. मतलब जहाँ पे भी 120 है, all of that light will vanish and you will get a black band. जहाँ पे भी 120. Why? Because all of this light was perfectly absorbed. Why? Because it exactly matches a gap. Okay, it exactly matches a gap. So because of that, this light is going to get absorbed and you'll get a black patch over there. So whenever you're going to pass visible light or even like the any kind of light, electromagnetic waves through an atom, certain wavelengths are going to get absorbed. Okay, depending upon the kind of atom that you have, certain wavelengths are going to get absorbed. So this kind of a thing is called as an absorption spectrum. इस चीज को हम लोग कहते हैं absorption spectrum. Some of the wavelengths in an absorption spectrum are missing. Some wavelengths are missing. So if somebody asks you which wavelengths are missing, the wavelengths that are exactly matching the energy gap between two orbitals are going to be missing in case of an absorption spectrum. If you allow all of the light to fall on the atom for some time and then you remove your light, यहाँ से तुम अपना light हटा दो, you remove your light. So all of the light that you were putting on the atom, all of the light you're removing, and you suddenly put these atoms in a dark room. So you're no longer providing energy. So basically क्या होगा, just like any kind of a moving object or just like any kind of bike, these electrons are going to come from outer orbital to the inner orbital. They're going to slow down, they're going to fall down. They're going to de-excite. Natural property of fault systems. If something is excited, if something has a large amount of energy, it wants to give up its energy and come back to a lower energy state or a more stable state. Okay, here your knowledge of chemistry is easily going to help you. So all of these black lines that you got, now these are the lines that are going to appear because the atom absorbed these wavelengths. Now you will only get these wavelengths. So you will actually get what is called as bright lines. All of these lines will be bright and the remaining space is all going to be dark because that light was not absorbed by an atom. So that light cannot be emitted. These spaces, they will all be dark. ठीक है, समझ में आ रहा है? ये सारे spaces, they will be dark. तो इस चीज को हम लोग कहते हैं emission spectrum. So an emission spectrum is just like the negative of an absorption spectrum, or the absorption spectrum is just like the negative of an emission spectrum. If you add both of it, then you get the total spectrum of light, the entire spectrum of visible light. So I hope you understood my entire discussion about what is an emission spectrum and an absorption spectrum. So it is these lines we are going to talk about right now. So the sun that we have, it is entirely made up of hydrogen. That is something that we know. And this guy called as Johannes Balmer, he came up with this thing that he observed, he observed that there are some specific wavelengths that are missing when you take out the spectrum of the sun. So when you take sunlight and you put it in a prism and you very carefully find out what wavelengths are present and what wavelengths are not present, it requires a lot of care. You just can't casually put a prism and find this out. So he found that certain wavelengths are missing. Lyman, another guy, inspired by the research of Balmer, he found out that some other wavelengths are also missing. So you know what I'm going to say. Passion. Okay. So one person finds out something, other people, they also want to come and try that thing out also. So Passion found out that some other wavelengths are missing. Brackett found out that some other wavelengths are missing. So ऐसे करते करते, people found out that there are some lines of the hydrogen spectrum that are known to be missing. So these lines were named after these guys. Lyman was named these lines were named as Lyman lines, Balmer lines, Paschen lines, Brackett lines, Fund lines, so on and so forth. We now understand that all of these Balmer lines are formed when an electron jumps from any orbital back to the second orbital. When it jumps from any orbital back to the first orbital, we get Lyman lines. When it jumps from any orbital to the third orbital, we get Paschen lines. And when it jumps from anywhere to the fourth orbital, you get Brackett lines. You get Fund lines when it jumps from anything to the fifth orbital. Okay. So when an electron jumps from the nth orbital to the first one, you will always get a Lyman line. Always it's a Lyman line. it falls in a particular range. We'll also calculate the range today. Then it jumps to the second one, you have a bracket line. So now you you have a Balmer line, I'm sorry. So now you get the idea clear. Okay. So let's find out what these lines are. So you have the hydrogen atom, and you have the first orbital, the second orbital, the third orbital, and the fourth one. So this is 1, 2, 3, 4. What is the smallest jump we can have? We can jump from 2 to 1. What is the largest jump you can have? You can have a jump from infinity all the way to 1, something that is called as electron capture. So we'll talk about electron capture, then we talk about X-rays. And if it jumps from one orbital to infinity, it's called as escape. Obviously, the opposite of escape is capture. So as I had, this is all about atomic structure. We are talking about all these lines. So before we go forward, let's talk about the orbital energies. 13.6 electron volts, 3.4 electron volts. How am I calculating this? 13.6 divided by n square for every orbital in the hydrogen atom. So n is equal to 1, 13.6. N is equal to 2, 3.4. If you put n is equal to 3, then you will get 1.5. If you put n is equal to 4, you will get 0.84 approximately. If you put n is equal to 5, you will get minus 0.5 something, so on and so forth. ठीक है, समझ में आया? तो ये सारे ऑर्बिटल एनर्जीज हैं. Smallest jump you can have is from 2 to 1. So let's talk about all these Lyman lines. So the smallest amount of energy gap we have is 3.4 से लेके 13.6. So what is this energy gap equivalent to? It's equivalent to 10.2 electron volts. What is the exact wavelength it's equivalent to? You know how to calculate this. So you can calculate lambda for the 2 to 1 jump in the Lyman thing as 1240 divided by 10.2. That's approximately going to be around 118, 20 nanometers approx. That is the smallest possible jump. Keep in mind that each jump is a particular amount of energy. So smaller the amount of energy, greater the wavelength. So this is the largest Lyman wavelength. This is the largest Lyman wavelength you can have. Okay? Because it is the smallest jump. What is the largest jump? You can come from infinity, which has an energy of 0. If you put n is equal to infinity, no negative or positive. So the amount of energy in that jump will just be 13.6. So what is the largest value of lambda you can have? Infinity to 1. That's 1240 divided by 13.6, which approximately turns out to be approximately 95 nanometers. This is your smallest Lyman wavelength. ये आपका smallest Lyman wavelength है. So Lyman lines, they lie in a particular range. They lie from 95 nanometers to somewhere around 120 nanometers. So this is called as the Lyman region. As you can see, the visible light region starts at 400 nanometers. So all of the Lyman lines, they lie in the ultraviolet range. Okay, they actually lie in the hard UV range. So Lyman lines, they are electron transitions from the first orbital. Keep in mind what I said. There is a small limit and there is a maximum limit. So these are called as the range boundaries or the range limits of the Lyman. ठीक है, समझ में आया? तो यही सेम चीज हम लोग बामर के साथ भी कर सकते हैं और करके भी देखते हैं. सो इन द केस ऑफ बामर लाइन्स, you are talking about a jump from the second orbital. So N2, you're talking about a jump from N2. The smallest jump you can have is N2 to N3, and the largest jump you can have is N2 to infinity. So what is N2? N2 is equal to 3.4. What is N3? N3 is equal to 1.5. So that jump is approximately equal to 2 electron volts. This jump is approximately equal to 3.4 minus 1.5, approximately 1.98. और सबसे बड़ा जंप जो होगा वो 3.4 इलेक्ट्रॉन वोल्ट्स का हो सकता है. What is the largest Balmer wavelength you can have? Least amount of energy. Take the least amount of energy, 1.9. So 1240 divided by approximately 2. That is around 620, 630 nanometers. And if you take the smallest wavelength, which means the largest amount of energy, take this one, and you divide 1240 divided by 3.4, which is just slightly less than 400 nanometers. This is just in the UV range, whereas most of the Balmer lines, they lie in the visible range. This is why these lines were discovered first. Visible, so people obviously thought they saw it, and that's why they discovered that there are actually lines. And then people started looking for other lines. Okay. So Lyman lines, Balmer lines, Bastian lines, bracket lines, Bund lines. All of these lines, these wavelengths can be found out experimentally. like we just found out right now. Okay, we found out all of these wavelengths by manually, like, understanding what is going on. It's jumping from here to there, and that is how these wavelengths are formed. James Rydberg came up with a formula for these things. He said that whenever these lines are emitted, we have photons. And these lines, they represent some final energy and some initial energy. So minus 13.6 z square divided by n square final, minus again that same thing, orbital energy, minus 13.6 z square divided by n square initial. So he said 1 by lambda is equal to minus hc divided by, not hc divided by, sorry, h into c multiplied by 13.6 multiplied by z square into 1 by n final square minus 1 by n initial square. In general, you can write 1 by lambda is equal to minus rz square. So he came up with r. Even before he knew that there is hc and there is 13.6, this guy comes up with r. And he says it's rz square divided by 1 by n square minus 1 by ni square. This formula is called as the Rydberg formula. And there is something that's called as the Rydberg constant, 1.11 into 10 to the power 7. So if you put in the values of n1 and n2, then you will get all of these different wavelengths for all of these different electrons. And the Rydberg formula was discovered even before the Bohr model of the hydrogen atom was well known. So that is why, in his honor, that constant is called as the Rydberg constant. It was a very important step in understanding that the structure of an atom actually has orbitals in it. So what is n is equal to 1? It's an orbital. What is n is equal to 2? It's another orbital. So the idea of orbitals actually comes from Rydberg's formula. Okay. सो सब तुम्हें समझ में आ गया होगा, स्पेक्ट्रल लाइंस होते हैं, एनर्जी होता है, एनर्जी फिक्स्ड होता है, ये सब चीज़ होता है, ये सब तुम्हें समझ में आया होगा. In the next class, what we'll do is we'll pick up all of these problems and we'll try to see which formula fits in where and we'll try to solve them. तब तक एक काम तुम कर सकते हो. You can try to understand and find out the energy of all these different atomic orbitals. Just remember 13.6 is the energy for an hydrogen atom. And you should be very good at doing z square by n square. So you can find out the first orbital, the second orbital, the third orbital, fourth, fifth, sixth. Quickly you can do it, and you can easily solve questions in an exam. If you actually sit down and remember and derive these things, it's going to take you a lot of time. Okay, so that's my advice for you. Goodbye.